Hi everybody, in this video I want to do a two-dimensional vector analysis problem. So here's the problem. Imagine I've got a north, south, west, east grid. All this is on the surface of the earth. Let me take east to be the positive x direction, north to be the positive y direction. Alright, so imagine that home is at the origin of this coordinate system. And I go through two successive displacements. First I go from home to work, and then I go from work to the store. So let's imagine the displacement from home to work is 4 kilometers in the direction 30 degrees south of west. So what do I mean by 30 degrees south of west? I mean from west, orient yourself 30 degrees south, so you're now 30 degrees south of west, and then from your starting point, walk in that direction 4 kilometers. Great. So that's home to work. Now, I have another displacement from the work to the store. So from work to store, I've got displacement of 3 kilometers in the direction 70 degrees north of east. 70 degrees north of east would be from east, orient yourself 70 degrees northward, or equivalently, this direction could be expressed as 20 degrees east of north. So from north, orient yourself 20 degrees east from there, walk in that direction, a distance of 3 kilometers. Great, so I've got that displacement written here. So in this problem, what I want to calculate is my net displacement from home to the store in that trip. So this is a vector addition problem. I've got vector A plus vector B gives me vector C. All right, and remember, graphically, we add vectors tail to tip. So here's my first vector, and then the second vector I put the tail of the second vector to the tip of the first vector. So vector A plus vector B, and then the net result is from here, from the beginning of vector A to the end of vector B, I'm calling that vector C. All right, so I can write the vector equation. Vector C equals vector A plus vector B. All right, so when I say I want this displacement from home to the store, I want to find vector C. All right, so we're going to work with the method of components. So if this is the case, if vector C is vector A plus vector B, I can also write that same thing for the components. So C sub x equals A sub x plus B sub x. And I can also write C sub y equals A sub y plus B sub y. So let's do this. First, we got our vector A. We can break that into components. So I can show those components here on the board. Let me do that. So vector A is going to have a x component that's this way, or sorry, a y component. And then x component here. So this would be A sub x, which is clearly in the negative x direction, or the westerly direction. This thing here we'll call A sub y. If I wanted, I could have put the A sub x here, just showing the displacements A sub y, A sub x this way. It's convenient to show them here just to illustrate the problem. Great. While I'm at it, I'll break up my vector B. I use the same thing. Actually, I've already got a dotted line here, which I use as my northward line to calculate this, or to determine this 20 degrees east of north. All right, so I can shorten that up. B sub y, and then this here, dot, 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 would be B sub x. And even from this, from what we see here, we can look at and sort of conceptually verify these vector analysis equations. We got vector A plus vector B gives me vector C, but let's look at the components. The C component, the x component of vector C will be from here to here. Well, that's just this amount to the left, and then this amount to the right. So if I took this and then backed off this, it would give me this. All right, so we've got this amount in the positive x direction, this amount in the negative x direction. That leaves me with this amount in the negative x direction. Likewise for the y component, I've got this y component upward, I've got this other y component, which is negative downward, If I take this and lop it off of that, I'm left with this, and there's the y component of vector c. So that's the conceptual explanation of this here. All right, so let's calculate these components. So, a sub x will be the magnitude of vector A, which is 4 kilometers. I'll just represent it as A for now. And I could do this a couple ways. I could go the full angle from the positive x-axis all the way around to here. That'd be 180 degrees plus 30, so 210. So A cosine 210 degrees. Or I could go, and that'll give me the negative sign. The negative sign will come out of this automatically. Or I could say, well, let me just work with the amount. I'll just work with this 30-degree angle here. I'd have A cosine 30 degrees. That would give me the amount of this. And really this 30-degree angle, I can rewrite it down here as a 30-degree angle there. Or I could imagine this being up here, but let me just look at this triangle here. The amount of this thing will be hypotenuse times the cosine of 30 degrees will give me the amount of this overall as an absolute value. But looking at going from here to here, that's a negative x component, so I need to put the minus sign in by hand. Cosine of 30 degrees is going to be a positive number, so I need to put this minus sign in by hand. All right, so I can calculate that number. We'll do that in a moment. And let me just remind ourselves that this A is 4.00 kilometers. All right, we can do the same thing for A sub y. A sub y will equal A sine 210 degrees, or, now we got to be careful, A sub y also in the negative y direction. I could go A sine of 30 degrees. Hold your thought on the sine there for a moment. The sine of the sine. So A sub y is opposite to the 30-degree angle, so I could take this hypotenuse, or the magnitude, times the sine of that angle, get the length of this, but now I need to put in by hand that it's in the negative y direction. If you use the full angle from the positive x-axis measured counterclockwise, the signs, positive or negative, will come out automatically. But if you use the smaller angle, between 0 and 90 degrees, you need to put in the signs by hand. All right, so we can calculate those out. Those come out to, I'll just put them in right here, minus 3.464 kilometers. And this one here, sine of 30 degrees, is a half. So we've got, for this one, minus 2.000 kilometers. And I'm just keeping an extra figure for now. Great. All right, we can do the same thing for the x and y components of vector B. B sub x. Now, I'm going to do this a little bit differently. I'm not going to use the angle all the way from the positive. Well, I can. I will. I'll use the angle all the way from the positive x-axis. I could use this angle, the 70-degree angle, or I could use this angle, the 20-degree angle. Let me show how that works. All right, so B sub x, I could go B cosine 70 degrees. Let me show that. All right. So this B I could imagine down here, B sub x down here, and draw this over here. So I have a right triangle this way. B sub x would be the side adjacent to the 70-degree angle, which I'm not showing, but that would be a 70-degree angle if this is a 20-degree angle. And so this B cosine theta would give me B sub x. It would also, the positive sign would come out of that. Cosine of 70 degrees is positive, right? And B is positive 3 kilometers. All right, or I could go using this angle here and looking at this triangle. B sub x is the side opposite the 20-degree angle, so I could go B sine of 20 degrees. That'll also give me b sub x. And I got to be careful. If I'm using an angle less than 90 degrees, I'm going to put it in the positive or negative by hand. This is going to be in the positive x direction. That comes out positive. Magnitude of a vector is positive, so it comes out positive overall. So that's okay. And that all comes out to 1.026 kilometers. Finally, b sub y, I've got b sine 70 degrees, modeling this one. Let's show you how that works. I would have a 70-degree angle here. I'd have a right triangle with a hypotenuse here. A y component side opposite to the full 70-degree angle, and there'd be my b sub x. All right, so the side opposite the 70-degree angle, that would give me the b sub y component, or opposite gives you sine. All right, or I could go b cosine 20 degrees. Let me show you that. If I look at this right triangle right here, the b sub y side is adjacent to the 20-degree angle. Now I got to be careful. I'm using the smaller angle. I've got to put in the positive or negative by hand because I didn't measure this from the positive x-axis. I can calculate both of these out. They give me the same answer, 2.819 kilometers. All right, so just to summarize this, I've shown you a couple different ways you can go about doing things. If you measure your angles from the positive x-axis to the vector, the x component will just be magnitude times the cosine of that full angle. The y component will just be the magnitude times the sine of that full angle. And the positive or negative will come out of your calculations. If you use a smaller angle, for example, here or here, using the smaller angle, I'm going to get a positive number, and I need to make sure then I check and see that I'm getting the sign of my components correctly. So I needed to put the sign, the negative sign, in by hand here for both the x component, which is in the negative direction, and the y component of A, which is in the negative y direction. All right. Down here, I did something a little different. The first part, I did the same way. For here, I measured these from the positive x-axis. It's an angle less than 90 degrees, but it's also from the positive x-axis. So the positive or negative would come out of this automatically. But here, I used a different angle. I didn't measure it from the x-axis. I measured it from the y-axis. So people will say, oh, well, you got sine instead of cosine for the x component. Well, that can be the case if you've measured your angle from the y direction. You're just using a triangle. All right, so you've got lots of ways you can work these problems. All right, so let's put this all together. We've got c sub x, the x component vector c. That'll be a sub x, which gives us a negative amount, and b sub x, which brings us back positively back this way, which will leave us with just this amount. And if we do add this up, a sub x minus 3.464 kilometers plus 1.026 kilometers gives us minus 2.438 kilometers. And for c sub y, I've got a sub y, that's in the negative y direction, and then b sub y, which is the positive y direction. I go down that amount, I come up this amount, I'm left with this amount, and that's my c sub y. My c sub y comes out to be this amount plus that amount gives me 0.819 kilometers. All right, so I can represent already my vector c one of several different ways. I could represent it in terms of these components. So from origin, go 2.438 kilometers in the negative x direction, go 0.819 kilometers in the y direction, and that would give me my vector c. I can write that out in unit vector notation. And if you prefer I hat and j hat instead of x hat and y hat, that's fine. I hat, j hat, and k hat correspond to x hat, y hat, and z hat for the Cartesian unit vectors. All right, so that's one way to represent our answer. We can also write in terms of the magnitude and direction. The magnitude of the vector c, which I can write as a c without an arrow over the top of it, or I could write it as c vector between the two absolute value symbols, which doesn't mean absolute value of the vector c. What it means is magnitude of the vector c. That's what that notation means. This means the same thing as this. We get that by taking the square roots of the sums of the components. So c sub x squared plus c sub y squared. And just for completeness, if I had a z component, I could put that in there too. I don't, so I'm just going to cross that out. All right, so if I put those in and crank them out, so c sub x, when I square that, that gives me something positive. C sub y, it's already positive, but when I square it, it gives me something positive. Take the square root, gives me something positive. Taking the square root of a positive number, so that's a good thing. And I get for the magnitude, I'm going to round it to 2.57 kilometers. I probably should have rounded this to 2.44 kilometers minus and 0.82 kilometers, given the 2 decimal places in my initial information, but I'll just leave that here. Just make a note of that. I probably should have dropped a digit and rounded them. To get the angle, one more step. All right, let me just draw the components of these components in, just to illustrate them. And I'll do that, I guess I'll do that with this blue marker. All right, so here's the y component of vector c. I'm not going to put an arrow on it. I'm just going to try and dot it out. And here's the x component of vector c. All right, so x component of vector c is in the negative x direction. Y component of vector c, we get positive. So those are the amounts. All right, we got a right angle right here. And if I want the angle, all right, so this 2.57 kilometers, that gives you the magnitude of that. And let's just check that. This was supposed to be 3 kilometers, and I've tried to make a decent scale. This looks a bit shorter than that. It looks like more than 2, but less than 3, so at least that checks out. The angle I want is, let's put it in here in this color. Let me go for this angle here, theta. That would be an angle going from west heading north, so north of west. I could also express it as a west of north angle and go for this angle here, but I'll go for the north of west because it's straight up triangle. All right, the tangent of theta would be opposite over adjacent. So theta would equal the arctangent of opposite over adjacent. All right, so to go from here to here, I take the arctangent of both sides. The arctangent of the tangent of theta gives me theta. The arctangent of this gives me that. All right, now that is arctangent. The opposite side on this is just this, and I'm working with a physical triangle, so I could take the absolute value well, I'm just going to write it this way. The opposite side has a length, absolute value c sub y. The adjacent side has a length, absolute value c sub x, right? So this means I'll get a positive angle out because I'm working like with a, just imagine this to be a triangle abstracted out in space. I'm not worried about positives or negatives. Imagine positive sides. All right, so plug the absolute value of c sub y in here, the absolute value of c sub x in here, take the arctangent. If you do that, you'll get the angle theta equals 18.6 degrees. Now, what does that represent on our picture? What orientation? Like if I wanted to go from home to the store and I wanted to orient myself in this grid, I would orient myself west and then go 18.6 degrees north from there. So that's 18.6 degrees north of west. And if I want to then write that as a vector, I'm running out of space, so I'll write it right here. My magnitude and direction format for vector C, I would have 2.57 kilometers in the direction 18.6 degrees north of west. All right, and I will box that up. And I'll box this vector up as well, noting that I should have rounded this 1 decimal place earlier. All right, so that's a two-dimensional vector addition problem. A couple points, just a couple reminders. If you add vectors graphically, you add them tail to tip. So take your first vector, and then if you're adding another vector to that, you can do that graphically by putting the tail of the second vector connected to the tip of the first vector. And then to get the sum of the first vector plus the second vector, go from the tail of the first vector to the tip of the second vector. All right, so vector A plus vector B gives me vector C. Now, if I wanted the displacement from store to home, that would be a vector this way. That vector would be minus C vector. All right, so the negative of vector is just the same as the original vector, but in the opposite direction. Same magnitude, but opposite direction. All right, so if I wanted to get the vector from store to home, that would be 2.57 kilometers, but it would be in that direction. So if this is 18.6 degrees, that would also be 18.6 degrees. I could express that as from east, go 18.6 degrees to the south. So from the store to home would be 2.57 kilometers, 18.6 degrees south of west. And that vector would be minus this original C vector. Okay, I think that's about all I want to say. Thanks for watching.